Hello, today we're going to talk about allowable row operations and Gaussian elimination. So we're going to talk about those things, and we're also going to do a good example. We're going to end up talking about partial pivoting and what that is and why we do that about the largest pivot. So what we're talking about is linear algebra, and that deals with linear equations that are linear in the unknown. So here we've got two linear equations and two unknowns, x and y. You don't see an x squared, you don't see a y squared, you don't see an x times y. So the equations are linear in the unknowns. So the idea here is that we try to solve them and find, in this case, a unique pair of x, y that will satisfy both equations a and b. So there's a number of strategies for solving these kinds of equations. Here we're going to just do some row operations. We're going to replace the first a equation with a divided by 2. So if you take 2x plus 3y equals 25 and you divide through by 2, then you're going to end up with x plus 1.5y equals 12.5. And then if you replace b with a minus half of b, what that's going to do is it's going to eliminate that first term in the result. So we end up killing the x, and we end up with a being 3y minus 2.5y, so that's going to be half a y. We're going to have a is 25 minus b over 2, so that's 17.5. So that means we're going to end up with 7.5 for that b prime equation. So we're kind of making a step here, and then the next step might be to replace b prime with b prime times 2. So that gives us a y, gives us y straight away. So when we multiply both sides by 2, we're going to end up with 7.5 transitioning to 15. And we've really solved for y doing that process. And if we know y, then we can substitute y into the a double prime equation. And when we do that, we end up with x plus 1.5 times 15 equals 12.5. And then you can solve for x, and x is minus 10. So we end up with the solution of minus 10 and 15 by a process really of elimination. And this is a very typical way that we can do this, and it's sort of the basis of what we're going to talk about today. What are row allowable operations, and then what would be a strategy to implement a Gaussian elimination strategy. Okay, so here's our example system in three unknowns. So we're going to look at three equations. They are linear in the unknowns x, y, and z. And we're going to look at some different ways. First thing we could do is think about a matrix inverse. So a matrix inverse would be when I multiply both sides of this equation by the matrix inverse. What that's going to do is it's going to create an identity matrix on the left side. So it's just going to give me x, y, and z only, but the inverse on the right-hand side times 13 minus 6 and 14 will actually give me the solution. So we could use matrix inverse to get the answer. So in this case, the answer to x, y, and z would be 2.85 minus 1.95 and minus 2.725. So that x, y, and z would be the solution to this equation, the unique solution. So one way is matrix inverse, and we're going to use that as a guide to see how we can get it by Gaussian elimination as well. Okay, so this is how it might look if you were going to do this in MATLAB. You could first of all get the inverse by using the inverse function. So here's how I put in the matrix. So it's 1 minus 8 and 2, and then I got semicolon to end the row, and then 5, 2, 6, semicolon to end the row, and then 6 minus 4 and 4 to end that third row. So I've got the inverse, and then I can multiply it with the matrix of the star or asterisk. And then I've got 13 minus 6 and 14 as a column vector, and that gives me the answer. So that's how you would do it in MATLAB. Okay, so a little bit of background for row swapping. So what I do is try to show students, there's a way to show these equations, these same equations, in a scalar form if you're not comfortable with the matrix form. But I try to get students to be very comfortable. So these equations here are equivalent to this matrix equation. So I've got three equations with the x, y, and z sort of scattered about over here. So those are the same as this one matrix equation. I like this representation, and to me, to be honest, I see both of them at the same time. I like to actually just write it in this way. So this highlights to me that the x, y, and z are my unknowns. The scalar values that go into the 3x3 matrix, those are scalar known values. And then the solution side over here would also be known. So the only thing unknown would be in this column vector, the x, y, z. Okay, so again, this is the same as this. And what I want to try to show you is a progression of looking at row swapping. In this example, I'm going to swap rows 1 and 2. So if I take the middle row and write that first, that's what I've got. And then I take the first row and write that second, that's what I've got. And the third row stays the same. So over here, if I look at how I'm doing that with the matrices, it's the second row of the 3x3. The second row of the original is now the first row. The first row of the original is now the second row. So I've swapped the rows of the 3x3, and I have to swap the right-hand side as well. At minus 6 and 13 have been swapped. So I've done these allowable row swaps, and it's important to recognize that the same solution, I get the same x, y, and z, and I can show that by doing my inverse, and I do the inverse based on the row swapped matrix. Okay, so the 5, 2, 6 comes first, 1 minus 8 and 2, 6 minus 4, 4. And then I've got the 6, the minus 6, the 13, and the 14. And I do, yea, verily, get the same answer. So conclusion is the row swapping of pairs is okay to do without changing the answer. I think it's really important this time to pause for just a second and introduce the augmented matrix. What that is you start with the regular system that you're hopefully becoming familiar with, the matrix representation, and you take that 3x3 and you glue together an extra column and create a 3x4 in this case. So you have an extra column with an augmented matrix that really is bringing in the right-hand side. So it's a little bit of a shorthand. You lose the view of the XYZ, but at the end of the day, we always remember that we do have three unknowns that in the equations. Okay, so I wanted to introduce the augmented matrix so that you could see that you have the 3x3, and then you just have that extra column that's coming from the right-hand side. Okay, let's go back and take a look at how we can apply this with the row swapping situation. We could show it in terms of our 3x3 with the XYZ and then the right-hand side. We could do that, and we could put these prefactor matrices on the left-hand side of both sides. So the left-hand matrices here, what they do is they will swap the first and second rows effectively. Like if I focus on this one column, and I look at what it's going to do with that row. So I look at this column times that row, then what that's going to have is going to be 5. So it's really that column dotted with that row. The answer is going to be 5. When I dot this column with the second row, I'm going to get 1 because you're just pulling out that 1. And then when I dot this column with the last row, I get that 6, and so forth and so on. Now, when I go look maybe at the second column, and I take a look at that dot with the first row, it's going to pull out the 2. And then when I take this column and dot with the second row, I'm going to pull out that -8. And then this column dotted with the last row, I'm going to pull out the -4. This column dotted with the first row, I'm going to get the 6. This column dotted with the second row, I'm going to get the 2. This column dotted with the last row, I'm going to get the 4. So with the 1 in that bottom right-hand location, that's going to leave the last row unaltered. And then with the 1s in these positions, that's going to swap the first and second rows. So I multiply both sides by the same thing, and it's going to do the same thing on the right-hand side. It's going to swap the first and second rows and leave the third row unaltered. If I look at it in terms of the augmented matrix, it's going to do the same thing across, it's going to do the same thing, replacing or swapping the first and second rows and leaving that last row unaltered. Column by column, it does this. So that's what row swapping looks like with a prefactor coupled with how it operates on the augmented matrix. So this is like a powerful shorthand that you can use prefactor with the augmented matrix. Okay, so let's think about scaling rows now. So let's move on. I'm going back to showing, the scalar equations all distributed out. So this is kind of a lot of a mess here, but again, the matrix representation is very much more appealing to the eye. Very easy to pick things out, what they mean. Here it's a little bit chaotic, but they're equivalent for sure. So if I were to take the second equation and multiply by 10, what that would give me is 50, 20, 60, and then -60 for that second row. So I'm just going to multiply the second row by 10. That's it. So if I were to do that here, the second row would be multiplied by 10 in the matrix representation. So pretty straightforward there. I could go and look at prefactors if I wanted to. Before I do that, let me make sure that I get the same answer. So I do the inverse of the same matrix with the second row multiplied by 10, both in this location and that location. So I've got the inverse times that column vector on the right-hand side. I get the same numbers for x, y, and z. Okay, so looking at a prefactor type of situation, so just multiply the second row by 10. So if you start out with an identity matrix, that would actually do nothing, right? Identity matrix on both sides. On the left-hand side of both sides. You could do that, or you could just operate on the prefactor on the augmented matrix like I'm showing over here. So these are equivalent. And if you had an identity matrix, it wouldn't do anything. But if you put that 10, you change one of the diagonal elements to a non-unity number like 10, then that's going to operate on the second row. Because as you think about each column coming through and multiplying through the prefactor, it's going to only affect, that 10 here is only going to affect the middle row as you bring each column through. Like, for example, if you do 1, 5, and 6 times the first row, you're going to get the 1. And then times the second row, you're going to get 10 times 5 is 50. And then the third row is going to be 1 times 6. And let's pick up another one. So if I did the second column times the prefactor matrix, the first row there, that 1 would pick up the -8. And then the second row, the 2 would hit the 10, so that'd give me the 20. And then the third row would be -4 times 1 minus 4. So very simple prefactor, and you see how it operates on the augmented matrix like that. So again, very powerful. We could just add or subtract rows, same kind of thing. So I'm going to take and add the first and second rows together and see how that looks. So again, just kind of spread out here and kind of a little bit chaotic, even with the parens. If I do it in terms of the matrix form, very nice form there. And then I can see what the results are down here. And then of course, I can do the inverse of that, do inverse of 6 minus 6 and 10, and 5, 2, 6, 6 minus 4, 4, and then my right-hand side end up with 7, and then -6 and 14. So the second row and the third row, not changed. It's just that I've added the original first and second rows together. So that's what this is showing, that the answer is unaltered. If I were to do this with a prefactor, both in the the left-hand, right-hand side, or on the left side of both sides, if I were to do it that way, or if I were to do it just on the augmented matrix, this is what it would look like. I'd have a 1 and a 1 on that first row. So that 1, 5, 6 would be adding 1 plus 5 together. And -8, 2, 4 would be adding -8 and 2 together when you dot that in your first row. So that's how I'd get the 6 and the -6. And then the 2, 6, 4, 2 plus 6 plus nothing. So that gives 2 plus 6 is 8. And then the last one, I'd have 13 and -6 coming off of that to give me that 7. So that's how that would work. And then the 1 and the 1 there with other zeros would just selectively pluck out the second and third row, leave them unaltered. So that's how it looks, prefactor or augmented matrix, where you're just adding rows together. That's what that looks like. So all the same. Now, kind of like the most complex situation would be what's called a linear combination. And I'm just going to do something really crazy, very, very contrived. I'm going to take the first row and I'm going to replace it with the first row minus 2 times the second row plus 3 times the third row. That's just the first row, right? I'm going to leave the second and third rows unaltered. So that's what I'm going to do. And if I think about, I'm just going to look at maybe the matrix representation here, see if this kind of makes sense. So I'm going to take 1 times 1, so that's 1, minus 2 times 5, so that's 10, so that's going to be minus 9, and then I'm going to say plus 3 times 6, so that's going to be plus 18, that's going to be plus 9, so that's how I got that. And then over here, if I take -8 minus 2 times 2 minus 4, so that's going to be -12. And then I'm going to have a -3 times -4, so minus another 12, so that's -24. And then here I'm going to have a 1 times 2, I'm going to have 2, a minus 2 times -12, 2 minus 12 is -10, plus 3 times 4 is 12. Minus 10 plus 12 is plus 2. So I got that right. Okay. Let's see if I can fumble around this one too. What the hell? So 13 minus 6 times 2. So it's 12. So it's 25 plus 14 times 3, 42. So I think that's 67. That's right. So yeah, so just doing, some very contrived combination of the rows just to show, that you could do it. And then, I want to do the inverse of this mess, and then multiply it by the right-hand side. And yep, I still get the same numbers. So you see that, these linear combinations leave the answer unaltered. So you're able to do those. Okay. So here's how the prefactor works. I'll just focus on the augmented representation, and you can see that the 1, minus 2, and 3 are going to multiply the first row, second row, and third row sequentially. So if I do it a column at a time, and I've already done this with you, the 1 times 1 minus 2 times 5 plus 3 times 6. I've already done that. I've done all of these columns. I've already done to replicate or create that mutated row there. And then the second and third rows are the same. So there you go. So very powerful shorthand, and just kind of seeing how the prefactors work. I think that's important. Okay, so prefactor matrices shown for row swapping, scaling a row, replacing a row by adding and subtracting rows, replacing a row by a linear combination. You can, pretty much use any invertible prefactor that you want. I just generically call this allowable row operations. That's what I do. And then I said, I could do all of these. I could do them in order. I could swap the first two, scale the second, add the first to the third. I could do a bunch of these things all running together in multiple. And when I multiply these three matrices together, I get this matrix, and I still have the same augmented matrix. That's going to create this augmented matrix. Now, what I could do is take this same, unaugmented, if you will, pull that 3 by 3 out, and then put this other mess over here. So I could go through and try to figure out from this system what the X, Y, and Z would be. And, you would see, if I were to do that I would get the same answer. Okay, so Gaussian elimination strategy. What we want to do is we want to put together our augmented matrix, and we want to get that. We want to do some operations on it so that 3, in this case 3 by 3, it becomes what's called a upper diagonal matrix. So I want upper diagonal matrix. And then once I get that, then I can go back to this form and then do a backward substitution where I can solve for Z first, then Y, because I would know Z, and then I solve for X last. So that's what we're going to try to do here. So we want to try to figure out how to do these prefactors in a strategic way. And this is when we come to find out about what's called a quote unquote pivot, and then we're going to figure out what partial pivoting means as we go, and then we'll figure out why do we do it like that. Okay, so we're going to take our example system that we've been dealing with, and we're going to write it as the augmented augmented matrix. Okay, we're going to do that. And then we're going to observe something here. We want to we want to move things around so that our first pivot is the largest by magnitude. Okay, so we're going to want this what's down here. We want that 6 to be up here. We really want that. So we want to swap the first and third rows. So to do that, I put my prefactor matrix like this, and that's what this does. And sort of saw this before. You start with an identity matrix, and then you say, well, I want to swap the first and third rows. This is going to leave the second row unaltered. So that's exactly what happens. The 6 minus 4, 4, and 14 go to the first row. The 1 minus 8, 2, 13 go to the last row, and the second row stays the same. So that's what we want. Okay. So now, we're ready to kind of pivot here. We're going to pivot about that 6. And here's how you do it is you want to start with an identity matrix like this. And we're going to clear under the 6. We want to make those a 0, 0. That's what we want. And in order to do that, then we're going to, in our prefactor matrix, we're going to want certain numbers in the A and B position. We're going to want that. So it's up to us to figure out, what does the A and B need to be, so that when I go over here and see what my next augmented matrix is going to be, that the thing that's under the 6, well, because of that 1 is 0, 0, you're going to end up with the same first row. But what's under that transformed 6, I want that to be 0, 0. All right, so how do we do that? Well, if you think about 6, 5, 1 multiplied by the second row, you're going to get 6a plus 5 equals 0. You can solve for a. It's simply minus 5, 6. So you're going to be pivoting on that 6. So the 6 is going to be in the denominator over here. All right, so let's see what happens with the b. So for the b, you want 6b plus 1 equals 0. You want the first column with that third row, you want that to vanish, equals 0. So b is going to be minus 1/6. Okay, so that's going to work out, and we go through and do our matrix multiplication for the second, third, and fourth columns, and I get this. I would encourage you to generate this by hand, just doing fractions. I think it's really worthwhile to see what that kind of looks like. So we have made progress. We have pivoted about the largest 1, 1 pivot, and we cleared under it with this prefactor. We have zeros and zeros there, so we are in good shape now to go to the next step. So the next step is we want to put that 44. We want to swap the second and third rows, because we want that bigger number by magnitude to be in that 2, 2 position. Okay, so we want to pivot effectively about 44 is what we want to do. We want to pivot about that. Okay, so to do that, we're swapping the second and third rows. So the prefactor looks like this. First row unaltered, swapping second and third row. Very, very straightforward. So that row becomes there. This row goes there. And we are now going to be ready to pivot. And we want to clear out what's under the minus 44.6. We want to clear that out. To do that, we're going to start with an identity. We want to clear under this, so we're going to want some kind of number there, C. We want to figure out what C needs to be so that we get the answer to have a 0 over on the right. So what that means is C times minus 44/6 plus the 32/6. We want that to vanish. So what that means is C is going to be 32 divided by 44. So that's what that means. All right, so we'll put that in, the 32 divided by 44, and then we go ahead and carry out the matrix multiplication. If you see 1 and a 1 there, the first 2 rows are going to be unaltered, and the last row is going to have that position cleared, and then we're going to have values there that we need to calculate. And this is what I did. This is how I presented it. So first two rows unaltered. Then it, kind of gets a little unwieldy there, but not too terrible. And when I show them like this in rational values, these are perfect. These are exact. These aren't round. There's no round off. So I try to avoid doing decimal representations to keep this kind of going. And I think I even, kind of cleaned that up a little bit. I try to make it where, do some simplification here. So there's the end result that I get. The last row admittedly has the 6 and the 44 in the denominator. I could clear that out, right? I mean, I could. Allowable row ops would be to multiply the second row by 6, clear that out. Multiply the third row by 6 and 44 to clear that out. I think that may be the way to go here, but I didn't kind of add that in the presentation. I've just left it with the swapping of rows and then the clearing under the pivots. So that's what I've done. So if I take and now do decimal representations, you kind of see what I had. I had 64 sixths, so that's 10.6667, or however I want to represent it. And then the 960 over 6 times 44, that's 3.634, 6364, and so forth and so on. So I've got a decimal representation. So now I start to lose accuracy if I don't carry enough decimals there. But anyway, I could go to a situation where I kind of put these together all on one page. So I have, the first augmented matrix where I swapped rows 1 and 3. I get that. I take that down here and I clear under the first pivot. I get this. Bring that down here. Swap rows 2 and 3. I get this. Clear under the second pivot, I use this. So you can start to see that is the resultant or the final augmented matrix. And now I have this represented by concatenating, multiplying all these in order. So I have the original matrix here, the original augmented matrix. And then on the left, I'm multiplying by that. And then I multiply again by the clear under pivot. And these multiplies are going towards the left, so you have to make sure you have the order right. Correct. And then swap the second and third rows, and then the last one is where I clear under the second pivot. So the order of these matrices is very important. And you see I get that final augmented matrix. Okay, so I could take that final augmented matrix now and do my backwards substitution. So here you can see that I've got the z, solve for the z at first, and I get that minus 2.725. And then now that I know that, I could go and solve for y from the second equation. So I'm going to have the 10 and 2/3, I guess, minus 1.1, basically 4/3 times my z minus 2.725 divided by the minus 7 1/3, and I get the minus 1.95 that I had earlier. And then once I know the y and z, I can solve for x with the first equation of the first row. So you see I would have 6x. So I've got 6 in the denominator. I have to divide through. Got the 14 minus 4 times z. That's from that. Minus 4 times z. And then I have a plus 4 from that guy, bringing that over, times y, which is minus 1.95. Anyway, and divide all that by 6, and I get the original x, 2.85. I think there's two reasons why we do the row swapping, so that our biggest pivot is what we're pivoting about, if you will. And one thing is, well, first of all, you can't pivot about a zero because you would be dividing by zero. You can't do that. But as you tend towards having that zero, you might have a big number. I called it big here. And then you take that big number and you divide by a very small number when you're trying to divide by a small pivot. And you might you take that to the big numbers, 2 to the 600 power, and you divide by 2 to the minus 2 to the minus 600 power. So big divided by small. Look at this. You end up with infinity. So it's an overflow situation where you take a very big number and you divide by a very, very small number, and it just kind of blows up. So you don't want to do that. You want to divide a small number by a big number. That's going to actually be more accurate too. So yeah, we can't do this. It'll just blow up. But if you remember what I taught you with floating point round off is the difference when you're adding two numbers. When you add two numbers, the floating point error is going to be bound by the sum of the individual things you're adding, each absoluted times machine epsilon. Or if you multiply two numbers together, you're going to end up with a floating point error that's equal to the product of the absoluted numbers times the machine epsilon. So what I taught you before is that you want to add the small numbers first, or multiply the small numbers first if you have a sequence of things that you need to add and multiply. Similarly, when you have division, the error in floating point division is going to be bounded by x, the numerator divided by the denominator, each absoluted, times machine epsilon. So if you divide by a small y, then that makes this possible error bound bigger. So you want to divide by a big Y, the biggest you could, and that's going to make the floating point error the smallest. And this is why we do the partial pivoting about the largest pivot. Okay, so partial pivoting. Partial, it's called partial because we're only doing row swapping. We're doing that with the prefactors over on the left-hand side of the augmented matrix. We're not doing a full pivoting. So full pivoting is when you're also swapping the columns. And to do that, you'd have to swap the X and the Y and the Z's around too. So that gets a little bit unwieldy. So we just do partial pivoting, which is very easy to do, as I've shown you. So partial pivoting, to do that, we do row swapping, and then I showed you how to clear under the pivot. And you are set up for Gaussian elimination like no one on the planet. I hope you thoroughly enjoyed it.